Okay.
Aí,
Okay.
tá gravando.
So good morning, everyone. And today, I will be talking about structured cospans, open systems, and all of that. This is mostly work due to Baez, Cristina Vassilakopoulou, and Kenny Parser. And I think it's very interesting. And this is mostly, I've studied these things mostly due to the Agile School of 2021 in the work group of Simona Paoli with Marisa Razzola, Elise Macaroni, and others. And quick disclaimer, what we're going to talk about today isn't exactly what was in the abstract. And this is like the actual abstract. Can systems be studied compositionally? In this talk, we deal with the problem, the machinery of structured cospans, and the double categories they form. We'll also describe how different models for n categories might elucidate further directions for this program. And this is because, in principle, I would talk about decorated cospans, which are like another model for open systems, and which is actually in like all applications, decorated cospans are equivalent to structured cospans. But for time reasons, I thought it was better to just scrap that. But after the talk, we can talk about them and say how they're equivalent through the Grothendieck construction and so on. Okay.
O que é equivalente?
And another model, which is that of decorated cospans. Today we talk about structured cospans, and then there's this other model, decorated cospans. We can talk about this after the talk. So this is the rough outline of the talk. You have some motivation. Then I won't assume anything on double categories. I will say the things we need to think about on double categories. And then the point is that we have double categories of structured cospans, which we can think of as double categories of open systems, and delve into some applications. Okay, so some motivation. That is a training topic in ACT communities that like open systems, and an open system is like a system that will interact with other systems. So this can be, for instance, this is like two pictures I got in the internet that are not from category theorists, but they like resemble the kind of thing we're trying to do. Like if you have like a reaction mechanism, chemical reaction like this and like this and like this, A plus B takes to C plus D and C plus B and so on. So what is this? So this chemical reaction will take AB and split CD at the rate K1. But another thing we can do is take CB and produce E plus D in a rate K2. So the idea here, in principle, these two chemical reactions are like disconnected. But so we would only have like this part of the graph, or like this part of the graph. The idea is, can we frame a language so that like chemical reactions can be studied compositionally? Like if you have this chemical reaction, you have a language that will split like the composition of two chemical reactions and so forth, something like that. Another example is this. This is a Petri net. We talk about these things, and this is just a mechanism to ensure that no two locks are locked at the same time. And what they do is that you have like this system here. You have like this system here. And the idea here is that this system can be composed with the other system by doing a push out, something like that. So this is like composition. This is like a push out. And this can go forward. You can study like, and this has been applied to like COVID disease spread models and yeah, and mostly the idea is that study these systems and try to develop a language in which we can always compose things in the most natural way. So like the toy example, so when we say this, what we'll actually talk about today are models with inputs and outputs. And the toy model to keep in mind is like an open graph. An open graph with inputs and out is a graph with inputs and outputs. So some nodes are marked as inputs and others are marked as outputs. So for instance, we have like this set of inputs here. This set of outputs here. And this is like our system. And so this graph here is marked like it has two markings of inputs here and two markings of outputs here. And you will see why, but this can be interpreted as like this is an open graph. This is a graph where you can plug in another graph using this input. So like if you have another graph here, you can plug in, you can like glue these two graphs, compose these two graphs by doing a push-up construction. So this is the main idea here, and this will be like always the picture to have in mind, that you have like set of inputs, set of outputs, marking your system as inputs and as outputs. And so such open graphs can be composed by connecting, by gluing outputs to inputs. So for instance, we have this open graph here, which has like these two markings on this node, these markings here, this marking here, here. So this is an input of this graph, this is an output, and this is an input of this graph. So they are marked by the same set of inputs slash outputs. And so the idea is that we can compose these two graphs by identifying along this map here and identifying along this inclusion here. So this three nodes will be like glued together, and what you get is something that looks like this. So this is like composition. And again, this will be like the idea will generalize in the general case. And actually we have more. That there is also a binary product on open graphs that is obtained just by putting them side by side. So if you have like this open graph here with these two markings here and so forth, so on, we can like tensor these two open graphs by putting the output side by side, by putting the graph side by side. And so this will be like a tensor product of open graphs. If you have like two elements here, we have 4 elements here, just put them side by side. Take the disjoint union over here, and so the disjoint union of the graphs, and so on. This is like a coproduct, tensor product. And of course, what we want to say is that this composition is really a composition, and that this tensor product is actually a tensor product. And this is true, that there is actually a symmetric monadic category of open graphs, and the objects are finite sets. So these sets here are the objects in your category, and the morphisms are these isomorphism classes of open graphs. So the morphisms are the open systems, and this will be in any model, any cospan model of open systems. This is more or less a paradigm that we have sets as objects and like open systems as morphisms, or isoclasses of open systems as morphisms. And okay, so of course, I haven't told you what is an isoclass of open graphs. And to actually say what is an isomorphic class of open graphs, we have to like say what is a morphism of open graphs. And to say that a morphism is an isomorphism class, we read like this is probably a two category, this is probably a bicategory. And in fact, it is. So we can actually define morphisms between open systems, which will look like this, for instance. So we have like this open graph up here, and we have like a morphism squishing this open graph, squishing B and C to E here. This is the kind of thing that looks like a this is a graph morphism by definition. And so this graph morphism in the middle has to be like compatible with these inputs and outputs. So this must be sent to this one because it's marked like this. And so on. So of course, what this picture is suggesting, that we have a bicategory where the objects are again finite sets. The morphisms here now are open graphs, not isomorphism classes of open graphs, but open graphs. And we have two morphisms, which are these open graph morphisms. And here the bold font didn't go off, but okay, there's another. Let me put a note here. Okay. So there is a bicategory of open graphs. This is true again. But actually, more is true. There is a symmetric monoidal bicategory of open graphs. And this isn't actually a trivial definition. This is like a hard to write definition. It has so many coherence diagrams, but it's true. There is a symmetric monoidal bicategory of open graphs, and it's compatible with our previous construction. So this is like bicategory modulo two morphisms. And even more is true if we allow like for maps between the inputs, instead of saying that this map here must be compatible with the inputs and outputs, you like flex that out by allowing for a map between the inputs, a map between the outputs. So the graph morphism must be only compatible with respect to this map. So this guy here must be mapped to the same guy through like this. It's like a commutative diagram.
I don't get what do you mean by underlying by category?
Sorry, this is underlying category.
Okay.
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 This is like open graph modulo two morphisms.
Okay, I get it.
Yeah, like
Yes.
and okay. So I will of course say what a double category is just now. Well, actually a pseudo double category. But the idea of a double category is that you have objects and you actually have like two flavors of morphisms. So you have like a horizontal morphism and a vertical morphism. And the two morphisms are the two cells are like squares in your double category. We'll talk about this. So the theorem is that this is also true. There is a double category of open graphs, and to every double category we can create a bicategory, again by quotienting out something out, and its underlying bicategory is open graph. So this is like that red open graph. Okay. So just have that. Okay, this is duplicated. And long story short, what we will try to explain today is how this can be all formalized using structured cospans and like writing the same pictures, the very same pictures we wrote like this. That a structured cospan for a functor here is a morphism of cospans that looks like this. And so for graphs, for instance, this will be a functor here from finite sets to the category of graphs. This functor here will send like a set S to the graph with no edges and S as nodes. And this is a structure cospan, so it's a cospan whose feet are like in the image of this functor. And the main theorem is that, like, in a very mild condition, that if L preserves coproducts, then structure cospans form a double category. And this is like very resemblant of there is a, and like Bruni will know this, that there is a bicategory, there is a double category of just cospans. And so the idea here is just with a Math theorem show that this double category is that you can change the fit to this condition and it is still a double category, and see that this is again symmetric as we wanted. And this is very complicated, but not so much. Okay, so a few definitions are in order for double categories. And as I said, a double category has like objects, vertical morphisms, horizontal morphisms, and like squares of this shape. So a square will have like a domain, a horizontal morphism. So the thing here is more or less, the definitions are like hard to write. This is actually so like equivalent definition. This will be almost true because of the pseudo word here. Pseudo equivalent definition is that double categories are just like categories internal to cat. You can check this out. It's like fun exercise to do. And so here in a double category, the two cells, the squares, they have like this horizontal domain in each, and have like this vertical domain here. And like this lives in a category, and the horizontal morphisms live in another category, and like vertical morphisms are also in a category, in a weak sense, perhaps. And what I mean by this is that we have like a vertical composition of two cells. And so this vertical composition here implies that there is a composition of vertical morphisms. And there is also a horizontal composition of two cells, which also implies that there is a horizontal composition of horizontal morphisms like this. And in the word pseudo here, it says that horizontal composition and only the horizontal composition is associative and until only up to natural isomorphisms. So the vertical morphisms are still strict on the nose. So up here, for instance, if we have like gamma, beta, alpha, we have like this is equal to this, if we stack them together here. But of course, you know this, there's no reason for it to be in principle, like this is just this functor here, composition, apply here. First compose the first two, then compose what you got, or compose the last two, and then compose what you got, and you have a true cell in the end, a true cell in the end. There is no reason for them to be equal, but in the pseudo double category, they're like, there's like an associator here doing the comparison. And so there are coherence diagrams. There's like a pentagon diagram, and there is a trigon diagram again. And this is the main reason why coherence stuffs will get complicated when we talk about symmetric double categories and so on. So I'm gonna just rush through that. A bicategory is just like a two category, but associativity and unitality only hold up to natural isomorphisms. And from the pseudo double category, I won't write the word pseudo here again. We can get a bicategory by taking the globular two cells as two morphisms. Globular two cells are like squares whose vertical morphisms are the identities. So, like if you have this double category here with squares, horizontal morphisms, you can define this like a functor from double categories to bicategories, and you will send like a double category here to this like horizontal underlying double category. So we'll send this to the bicategory with the same objects, the same horizontal morphisms, but the two morphisms are squares of this shape. So we have like this functor here. Let's go image me. And of course, you can go from a bicategory to a category by quotienting out two isomorphisms. This is what I meant, Mike. So we have like in the bicategory, you can quotient F by G if there is a two isomorphism between them. Push, and you get a category. This is like a functor from Bicat to cat. So in the end, what we'll have is like a functor from here to here, and call this Q here from here to here. And so this will be like the three levels of that we'll have: categories, bicategories, and double categories. And we start here and go down. I won't say what a symmetric double category is. I would just say that this is like almost the same thing. Like you have a double functor from D times D to D and so on, but you have like so many coherence diagrams that it becomes really hard to understand, because for instance the associator here will be like a pseudo double natural transformation from this to this. So is this right? This is not right. You got it. Let me change. So, okay. So double categories of structure cospans, and the main theorem here it is that if this functor here preserves products, then there is a symmetric double category of structure cospans. So the objects, we call a structure cospan, looks like this. And so the objects are these morphisms here, like I and O. And the vertical morphisms are like the morphisms that I, or I and I prime. And the vertical morphisms are just these morphisms in A. The horizontal morphisms are structural cospans, and the two cells are commuting squares of this form. So the horizontal morphisms are structural cospans, and the two cells are like a pair, a map here, a map here, a map here, such that this commutes, this commutes. And then, okay. Just a quick word on why structural cospans form absolutely double category, not just double. It's because horizontal composition here is then choosing a push out. So we have like this structure cospan here. So this is like horizontal morphism from A to B, and this from B to C. And horizontal composition is done using this, taking this push out here. So okay, so it then is take this push out. And there are like two ways of composing like a pair of composable morphisms. So this will go from A to B. This structure cospan goes from B to C. And this structure cospan goes from C to D. And so we can either like, again, compose the first two doing this push out and compose the last, and then compose what you got with like this push out diagram here. Or you can compose the last two and then compose it with this. Sorry. Compose it here. So there are two ways of composing this. That's usual, but the point is that they are not equal. There's no reason for this to be equal to this, but the two are like co-limit construction. So there is a unique natural isomorphism between them. And that's why pseudo is a category. There will be like a unique natural isomorphism in this case between the two associators, but it will be seldom equal. I don't know an example where we have like this push out commuting on the nose, unless it's like a trivial example. Even just to fill up our desiderata, for open graphs are a structure cospas for this functor here. This functor will send a finite set to the graph with that set of nodes and no edges. So called if, for instance, if you have like this functor here, this element, this set here, we get sent to like a graph like this. And a structure cospan will look like this. It will have like a graph morphism from like a discrete set marking the graph and a discrete set marking your graph as inputs, marking outputs. And this preserves product, that's like on which product this is preserved. This preserves coproducts, right? It will send like a joint union of sets to like the disjoint union of these discrete graphs. So by the theorem, if all preserved products, there is a symmetric double. There is a symmetric double category of open graphs. And what is a morphism in this case? What is the two morphisms? Well, the two morphisms are precisely what we had in mind, what we wanted to do. And this will be like the form of two morphism, will be a graph morphism here, such that this commutes, and This function here, it's actually like what is the word? It's like a reflective localization of. So this is actually like here, and it has an adjoint, and so forth, so on. So this map here from Li to L through I prime actually corresponds to a map from between the finite sets below. This is not true in general, but so the two cells are these open. This graph is a graph. In fact, it's a graph morphism in the middle, such that this map graph marking the inputs here and this map marking the inputs here is compatible with this morphism here. Call it K. Call it A. Call it B. A and B. And this is F. So this will be like compatible. And everything I said in the introduction will like follow from this. Will follow from this double category. So composing will be just like composition, and tensoring. Composing will be like horizontal composition, actually, right? Because horizontal composition is that push-out construction. And tensoring by including stuff side by side. And the fact that this is a symmetric double category says that we can also like tensor morphisms, tensor two morphisms, and so on. And what I said in the introduction says that we can go from that double category to the bicategory of open graphs. And this is sometimes very useful to keep in mind, because bicategories are better studied than pseudo double categories. And and the picture that was missing here, right, is that this will be defined by this. This is like a definition. This. And what we'll have in the end is just like you have an identity up here, if you want. And if you go down to the category of open graphs, we like quotient out these open graphs by isomorphisms. And in the first paper on cospan approaches to open systems, we only had like this, an isomorphic like category. And the thing is that you can, if you have like quotient out isomorphisms, then you can work with open systems on the nodes. You can only work with like open systems up to an isomorphism class. So, for instance, if you have write something like for more or less like the chemical reaction of formation for CO2 will look like this. And the chemical reaction for forming water will look like this. So these things are like clearly isomorphic in any sensible way, but if we quotient them out, they have the same isomorphism classes, so you can't tell them apart. So it's a good thing to work at least on the bicategory. Okay, and I will move to some applications now, but do you want to ask anything?
After the talk, I want to bug.
Okay.
Good.
Okay, so application number 1 is open circuits. How we will model open circuits here? Well, let's model a circuit first. Like we'll talk about circuits like as R, like 0, infinity, labeled graphs. These are like fancy words, but this is what a circuit is. It's like a circuit like this, for instance. And then you have like 3 home here, 17 home here, 13 home here. What is this? We can interpret this like a label graph. Like this is a dot here, this is a node here, this is a node here, this is a node. So this is labeled as real numbers. And this is like an edge from node 1 to node 2 with label 3. This is an edge from node 2 to node 3 with label 17. This is an edge from node 2 to node 4 as with label 13, and so on. So I can actually change colors here. Sucks. So, okay, the idea is that in real life, we can do a few operations with circuits. For instance, we can, if we had a circuit like this maybe. And so this will have 6. Okay. We want to like be able to plug in, like glue these two together, these 3 and 6. So you expect to be able to write something like this. I won't write the labels anymore. Right? This is like trivial stuff in real life. This is like the kind of operation you want to do. And if you, so this will, we want to write this like as our horizontal composition of structure cospans. And another thing we could do is like considering like the disjoint union of these graphs. And so the disjoint union would be like tensor product. And of course, we will try to formalize this using structure cospans. It will be almost the same thing as in the introduction. We have a functor of infinite sets to like R labeled graphs. And this will send like the set, a finite set like this to, again, to the graph with these elements but no edges. And what is the structure cospan? In this case, the structure cospan will like mark. Let's see if I can try to select. Ain't working. Sorry. Okay, so all will be like a structure cospan here. It will be something like of this shape, Li, to the label, to the circuit from Lo. So this Li here will be like something like that. And this will mark like where can you plug in a new circuit. For instance, something like this as input. And the LO here, and this is like L2. And for the output here, perhaps you can only connect on this port here. So not like this, only this marking, for instance, L1. Right. And what we did back then was that we had something like this. And whatever we have. So this will actually go from A here, and this will have like another output. Perhaps it has. You can connect whatever here. And so, okay, so now we have like a double category whose objects are finite sets, whose horizontal morphisms are labeled graphs which we interpret as circuits, and the horizontal composition is gluing them together along these marked inputs and outputs. You compose a circuit with another. And what are the two morphisms? Well, you kind of maybe you wanted the two morphisms to be something like you have two parallel resistances and a two morphism exists between this and the equivalent resistance here, but you don't have that really in this formalism. There are like other ways of writing this down. And I was talking about this on Zulip the other day. You can do this, not a two morphism, not a two morphism. How you do this? I find it really interesting. You kind of define a power functor from this we'll have like a double category of open circuits and a category of open circuits. So I have this power functor from open circuits to another category D, whatever, such that then you will map like call this F, call this G. These are morphisms in your like representative morphisms in your category, so that F and G will map to the same guy here. And so we can like quotient open circuits by the equivalence relation this generates on morphisms. But yeah, two morphisms won't correspond to this. And this is actually sad considering the pictures that we have here. We really wanted to have like a two morphism from one side to the other. Nevertheless, we don't. And another example, I won't say much. Yeah, Petri nets are kind of cool. So a Petri net is like a graph where you have two kinds of nodes. and some are called, these circles here are called places. And these boxes here are called transitions. And why is that so? This is a Petri net for water formation, for instance. The idea of this Petri net is that this Petri net will like eat 2 hydrogens and eat 1 oxygen, and you move to spit just 1 water here. There are some cool examples on the internet. And for instance, this is like a Petri net, or have like these places, these transitions, and this just, you can go from place A to place B by firing these transitions. Okay. Like this. And there's this interesting example here. That, for instance, this is like a Petri net for like 2 semaphores, 2 traffic lights working in parallel. So you have like this. If you have a place here, like this semaphore is lit up green, this traffic light is red. You can't have like green and green at the same time, because then cars would crash. And the idea here is that you put a queue here, and this queue here won't allow for green and green to be lit at the same time. So this red transition to green, red transition to green, green transition to red. But since red takes 2 dots here, so you see now you can transition to green because this is like green. This is like a very smart way to write this down. And the thing here is that if you have like a 3-dimensional traffic light, or like a 3 intersection traffic light, how would you do it? You would just add another one on this queue here, and that will be like doing a push-up. So that's an example. Another example here will be like if you have this formation of water, and if you have what is yeah, I actually had the picture. And yeah, this is kind of the thing I wanted to have not here. I missed the picture, sorry. Is that if you have like this, like the formation of CO2, and with CO2 you can actually form another thing. NH, what is this? This is sodium bicarbonate. No, yeah, and so on. So you can actually try to compose like this chemical reaction with this chemical reaction with this chemical reaction. And the moral of the story is that this can be formalized using structure cospans for this functor sending a finite set to, there's a category of Petri nets. And this will again send like same thing. We send this finite set. We send like 1, 2 to the Petri net with this state, but no transitions. And we're running out of time, but I really like the idea just to say that like a double functor between different cospan structure cospan categories, it will like compare different open systems. For instance, we can have open graphs here and open Petri nets here. We can try to define a map from open graph to open Petri nets, and this will like compare a system to another. But it's not you won't only map an open system to another system. We will map the open system to the other system, and we will also map the composition to the composition. And so this is like and the two morphisms to the two morphisms, and this is like very compositional. And it's good to work like on the double functor here, because if we were to work now on the between the categories, we wouldn't be able to tell CO2 and water apart. So concluding remarks, we want to talk about map between open system. Double categories did pop up naturally to encode this information. And the symmetry in the underlying category is a shadow of the symmetry of the double category. But either way, proving that either the category or the double category is symmetric is really cumbersome. So what we're trying to do, one of the things we're trying to do, like with Simona and the others, is try to use another model for symmetric double categories in which we won't have to check like so many coherence diagrams. And the idea is that a symmetric monoid double category is like a triple category with one object, just like a symmetric monoid category is really like a Bicategory with one object. And we can actually try to dodge coherent diagrams if we think about this. If we use other models, there are other models. Simona has this other model that where she can work with like with double, triple, and so forth. Categories, bicategories, tricategories, four categories, and by check coherence like indirectly. And we're trying to see if we can apply this to structure cospans and perhaps go for higher end. And that's it. Thank you.
Okay, so do you want to do the discussion in English or Portuguese?
Yeah, I think we can end the recording right now.
Okay, so I'll stop the recording.